Let's try to visualize constructive interference and destructive interference using waves with equal wavelength and amplitude. So for example, you have these two waves, wave 1 and wave 2, and both of them have equal wavelength at this point and this point. If the wavelength of wave 1 is represented by lambda sub 1 and the wavelength of wave 2 is represented by lambda sub 2, if we assume that they have equal wavelength, that means lambda sub 1 equals lambda sub 2 and so on. Also, we assume that these two waves have equal amplitude. So for example, if wave 1 has an amplitude of A, then this wave 2 also has an amplitude of A. So if you measured it from the equilibrium position to the trough, then this is equal to negative A. And the same goes for wave 1. If you measure this length from equilibrium position to the trough, then this is equal to negative A. Let's assume this is the y-axis and it starts at its highest value or the amplitude, and then it reaches the equilibrium position, and then it goes to its trough and then rises again to its maximum value, and then to its equilibrium position, and then to its trough, and then rises to its crest, and so on. And the same goes for wave 2. In other words, wave 1 and wave 2 are in phase, meaning to say one of the waves do not lag behind by a factor like pi. So if we focus our attention at a particular point in time, for example, let's represent this as t sub 1. So at t sub 1, wave 1 has a value of negative A. So at this point, this is actually negative A. And also wave 2 has a value of negative A at time t sub 1. So if we try to superimpose these waves, in other words, we try to add wave 1 and wave 2, the resultant wave would look like this, and at time t sub 1, it has a value of negative 2A. So when we have waves that have equal wavelength and amplitude, then the resultant wave is actually in phase with these two waves, and at the same time, their amplitude is additive. On the other hand, if our two waves, wave 1 and wave 2, are out of phase, or in other words, one of the waves lags behind or advances by pi over 2, or if this x-axis represents position, then it lags behind by lambda over 2, then their resultant wave is actually 0 because, for example, let's name this position as t sub 1. For example, if the x-axis represents the time, and at t sub 1, wave 1 has an amplitude of negative A. And at t sub 1, wave 2 has an amplitude of positive A. When we try to add wave 1 and wave 2, then at time t sub 1, negative A plus A is equal to 0. So when one of the waves is out of phase with respect to the other wave, if we try to add these two waves, then the resulting wave would be 0. So in this case, we call this interference as destructive interference because you're literally destroying the presence of the waves. To clearly visualize destructive interference and constructive interference, we must have monochromatic waves with equal amplitude. When we say monochromatic waves, this means that the waves have equal wavelength. Ideally, they must also have equal amplitude. So let's now investigate the behavior of the interference pattern when we have a double slit interference. Now in this setup, you have plane waves propagating to the right. So from our previous discussion, we could represent plane waves with parallel light rays, like what is shown here. And in a double slit interference, like what has been done by Thomas Young, we have a slit S0 and it is passed through two slits, and we represent this slit as S sub 1 and the other slit as S sub 2. So we use S sub 0 to produce a spatially coherent wave. When we say coherent, so when the wave travels, it has a constant phase. So in order to effectively observe interference, when we let a plane wave pass through a single slit like S sub 0, then this wave diffracts like this. And we could represent these wave fronts as light rays. Remember in our discussion of wavefronts and light rays are always perpendicular with respect to the wavefront. These coherent plane waves can actually be produced by a laser. For example, there is actually a huge laser here. We use this laser to illuminate a single slit like S0, and the light passing through this S0 diffracts and passes through another slits S1 and S2. Now we do this because we want to produce two sources of light that have equal wavelength and amplitude. If we let these light waves pass through these two slits, we are sure that the light waves coming out from S1 and coming out from S2 are light waves that have equal wavelength and amplitude. So that's the purpose of this primary slit. It is to produce a coherent wave, and this coherent wave is passed through S1 and S2 to observe interference patterns between two similar sources of light. So again, the purpose of S1 and S2 is to produce coherent light waves that have similar properties because they actually come from a single diffracting light wave. So the distance between S1 or slit 1 and slit 2 is D, and the distance of this slit from a screen is capital D. Later, when we discuss diffraction, we also use the variable D to denote the width of the slit. And right now, S1 and S2 have slits that is very small in size to the point that it somewhat produces light waves that come from a point source. But since this represents slits, basically we could represent each point here as a point source of light. Now, when Thomas Young performed this experiment, he noticed that he's able to produce a distinct pattern of bright and dark bands on the screen. So we would like to represent this pattern with an equation, and this equation is derived by the physical dimensions of the slit and the distance of the screen. In actual experiment, it is easier to measure the slit distances and the distance of the screen rather than the actual wavelength of the light wave. And once we derive an equation for the relationship between the wavelength of the light and the physical dimensions of this setup, we could actually predict the wavelength of an unknown coherent light by measuring the different parts of the interference pattern with respect to the other physical dimensions of the slit and the screen distance. Again, by deriving this equation, we could actually predict the wavelength of an unknown monochromatic or coherent light by measuring the properties of the interference pattern and other physical variables like the slit distance and the distance of the screen to the slit. So to explore the relationship between the interference pattern and other physical variables, let's zoom at this setup. Let's introduce the concept of path difference, and we represent path difference as delta sub L. So don't mind these figures here. Let's focus our attention first with the fact that if this is the y-axis and this is the x-axis, but this horizontal axis represents time, and I have a wave starting from its maximum amplitude, then as it propagates in space, it behaves like this. And I have another wave similar to this wave. Then, no matter what point I choose, for example, at this point, at time equals 0, it has the same amplitude with this second wave. For example, this is wave 1 and wave 2. Therefore, if I try to compare the part of this wave 1 at time equals 0 and this part of wave 2 at time equals 0, they are equal, and this wave 2 do not lag behind by any non-zero phase, meaning to say they have equal phase. Therefore, the path difference between these two waves is equal to 0. However, for example, if wave 2 advances by pi over 2, like this, notice that at time equals 0, the resulting interference between wave 1 and wave 2 is equal to 0. Because the amplitude at time equals 0 is positive A, and the amplitude at time equals 0 for wave 2 is negative A. So if you try to add these two waves, assuming that they have equal wavelength and amplitude, then they will cancel out. So in other words, if the phase of this wave 2 lags behind or advances by pi over 2, then they cancel out each other. And if you try to measure, for example, the differences in their wavelength, then the path difference between wave 1 and wave 2 is lambda over 2. It doesn't actually matter if you view wave 2 as if it advances by pi over 2 or it lags behind by pi over 2, because they have equal wavelength and amplitude, meaning to say it's really hard to discern since the structure is the same. So the important thing is, when two waves cancel out, the path difference between them is lambda over 2, assuming that these two waves have equal wavelength of lambda. So again, when wave 2 and wave 1 have a path difference of lambda over 2, then if you try to superimpose wave 1 and wave 2, the resulting wave is actually a wave with zero amplitude, or it will result to a destructive interference. Otherwise, when the path difference is just zero, they behave similarly. At different times, they have equal magnitude of amplitude. Then, when you try to superimpose wave 1 and wave 2, you'll end up with a bright wave. So, when you try to superimpose two waves coming from two sources, what you will actually observe on a screen is a bright spot if you have a constructive interference. Otherwise, we will observe a dark spot or dark region on a screen when destructive interference occurs. So going back to our figures, if this is slit 1 and this is slit 2, and we just focus on one wave traveling from slit 1 and one wave traveling from slit 2, and instead of representing the wave with a pattern like this, let's just represent it with a ray. If these two waves interfere in a constructive manner, then we will have a bright spot here at point P. Otherwise, if they will interfere destructively, then we will have a dark pattern at point P. The distance between S sub 1 and S sub 2 is D, and the distance of the center of slit 1 and slit 2 to our screen is represented by this line. And this distance is represented by capital D. Point P is at a distance y from this center of the screen. We would like to derive an expression that actually help us predict whether at point P we will have a bright spot or at point P we will have a dark spot. We would like to derive an expression that describes the interference pattern that lands on this screen based on the physical dimensions small d, capital D, or y. So if our screen is relatively far from our slits, and this is achieved when d is very large in comparison with small d. And if we try to zoom in on these two slits, we have this figure. So again, when the screen is very far from our light source or the slits, the light rays coming from S sub 1 and S sub 2 are almost parallel or near parallel to each other. And based on this figure, if this is y and this is d, and we represent this with a giant right triangle, then we could actually measure an angle here as theta. And if that is theta, and since we are actually considering two light rays as almost parallel to each other, then we could also approximate the angle between the horizontal distance and the light ray as theta. And by similar triangles, the angle between this line and this line is also theta. If you try to visualize this as a right triangle, and this is also a right triangle, then these two right triangles are actually similar triangles. Therefore, if this is theta, then this is also theta. And notice that if we focus on this wave 2 alone, for example, this is the wave represented by this light ray, and this is the wave represented by light ray 1. Let's call this as light ray 1 and this one as light ray 2. Notice that light ray 2 already advances by a particular fraction of a wavelength with respect to wave 1. So the difference in this wavelength is called the path difference, and we represent it with delta L. Now, based on this figure, delta sub L is equal to d sine theta. So this is just pure trigonometry. And notice that from our previous discussions, if the path difference between wave 2 and wave 1 is equal to lambda over 2, then this will result to a destructive interference. If delta sub L is equal to lambda, meaning to say if this is wave 1 and wave 2 advances by lambda or one wavelength like this. So technically, if I extend wave 1, it is actually still in phase with wave 2. So even if wave 2 advances by 2 lambda, for example, if I multiply 2 here, so for example, this is one wavelength and another one wavelength. So it advances by 2 lambda. Wave 1 and wave 2 are still in phase. So in other words, if the path difference between wave 1 and wave 2 is just an integral multiple of m lambda, then this results to a constructive interference, and you will be able to observe a bright region on the screen when constructive interference occurs. Now, going back to this condition of destructive interference, if we represent wave 1 with this pattern and wave 2 is delayed or advances by lambda over 2, then obviously it will result to a destructive interference. But what if wave 2 advances by 3 lambda over 2? So I'll count 1, 2, 3. So if wave 2 advances by 3 lambda over 2, it will still result, because if we extend this to infinity, sorry, then this still will result to a destructive interference. Let's return to this condition of destructive interference. So for example, if wave 1 is represented by this wave, and the path difference between wave 1 and wave 2 is lambda over 2. So I'll count 1. Yeah. So count 1, 2, 3. If I try to add wave 1 and wave 2, and wave 1 and wave 2 have path difference of 3 lambda over 2, this will still result to a destructive interference. So in other words, if the path difference delta L is m plus 1/2 lambda, where m is an integer multiple like 0 or negative or positive 1 or negative or positive 2 and so on, then this will result to a destructive interference. So to summarize, if the path difference between two similar waves is an integer multiple of their wavelength, again, m here is an integer, then the resulting interference pattern between the waves is a constructive interference. And in an interference pattern, this is actually represented by a bright region. On the other hand, if the path difference between wave 2 and wave 1 is quantity m plus 1/2, where m is an integer multiple, then the resulting interference is a destructive interference. Now, when we have a double-slit interference, this path difference is equal to d sine theta, where d is the distance between the two slits. Again, we derive this expression by assuming that the distance between the two slits is smaller than the distance of the slits to the screen. Now, going back to this figure, we could actually also equate delta L. So I'll try to put a box on this one. So based on this figure, we could also calculate for theta. Tangent theta equals y over d. And from this, you could calculate for the angle and plug it here. In some problems, the distance of the screen relative to the slits are extremely large, and based on this dimension, we could actually approximate tangent theta as almost equal to sine theta. So in this regard, we could actually replace sine theta with y over d. This time, instead of having double-slit interference, we will now consider multiple-slit interference. So for example, let's focus on these three rays first. If at a particular angle, let's say theta, let's assume that with respect to this ray, the second ray has a path difference of d sine theta, and the third ray, with respect to this first ray, has a path difference of 2d sine theta. If this path difference is equal to lambda, and apparently this is equal to 2 lambda, then these three rays will produce a constructive interference on a screen. And this interference will produce a very bright pattern. So for example, if this is the screen, let's assume that it will produce a very bright pattern. Let's suppose that the path difference of this ray 2 with respect to ray 1 is lambda over 2. Then apparently, this one has a path difference of lambda with respect to the first ray. Let's name this as ray 1 and then ray 2. And this one as ray 2 and then this one as ray 3. Now, ray 1 and ray 2 will obviously result to a destructive interference because they have a path difference of lambda over 2, and also ray 2 and ray 3 will result to a destructive interference because their path difference is actually lambda over 2. However, when we compare ray 1 and ray 3, the path difference between them is one wavelength. Therefore, the interference between ray 1 and ray 3 will result to a constructive interference. This will result to a brighter principal maximum, and this time we will have a secondary maximum like this. Aside from having a principal maxima, we also have this what we call secondary maxima. And in between this principal maxima and secondary maxima is a dark region. So this time, when we are considering multiple slit interference, there will be a presence of principal maxima and secondary maxima, and in between them is a dark region or dark fringe. And when you try to increase the number of slits, the amplitude of the principal maxima increases in amplitude because there are more slits reinforcing or producing a constructive interference relative to each ray. If we return to our condition of d sine theta, the same condition applies that when the path difference between consecutive wave is an integer multiple of lambda, then this will result to a constructive interference. But when it comes to destructive interference, remember that the condition from double-slit interference is quantity m plus 1/2 lambda, where m is an integer. This time, there will be a presence of secondary maxima and in between secondary and primary maxima, there will be a dark fringe. Let's look at the interference pattern formed by soap bubbles. The interference pattern, so for example this one, formed by bubbles, consists of many colors. So let's try to choose a zoomed image of this bubble, like this one. So the interference pattern created on a bubble film consists of different colors because color depends on the wavelength of light. And notice that the variation of colors in the bubble is dynamic because the color that we see depends on two things. First, the thickness of the film of the bubble changes with respect to its position. So along the surface of this bubble, you'll be able to measure different thickness of its film, and also you are looking at the reflection of light at different angles. So again, the variation of color that you see along a soap bubble depends on the angle of reflection of the light wave hitting on that soap bubble, and at the same time, the thickness of the film of the bubble is not uniform. The interference pattern coming from soap bubble is actually dependent on the reflected wave given off by a soap bubble. For example, you have this soap bubble, and we just magnify a small portion of this soap bubble. Basically, soap bubble is just a film of water mixed with some molecules that has a hydrophobic and hydrophilic ends. So essentially, majority of the components of the film of the bubble consist of water. So basically, this is air. We could just simplify the discussion by assuming that majority of the film of the soap bubble consists of water, and inside this bubble is just simple air. The air and water don't have equal refractive index. So what actually happens if this is the eye of the observer, when light strikes the film of the bubble, some of it gets reflected and some of it is able to pass through this boundary and then gets reflected again. Let's derive an expression to predict that what we are actually seeing is a constructive interference or destructive interference. Recall that in this figure, when you see a bright region, even if it has the same color like this one, this means that constructive interference takes place when we view the light rays in this region, and destructive interference happens when we have a very dark region here. So let's have a general method of calculating constructive interference and destructive interference when we have a system consisting of a thin film. When light rays are reflected through a thin film, we could actually predict whether the reflected light rays will result to a constructive interference or destructive interference. Our incident light ray comes from a medium with a refractive index of n sub 1. So this light ray here is our incident ray. When this incident ray is reflected through this boundary, let's represent the reflected ray at this boundary as ray sub 1, and some of the incident rays actually able to pass through this boundary, and some of such light rays is then reflected again on this boundary. And let's represent the reflected light ray from this boundary as ray sub 2, or just simply 2. Now this time, since we are dealing with reflected light rays, we should examine first whether such reflected light ray is reversed or out of phase with respect to the incident ray. Remember from our previous discussion that when an incident ray or incident light being reflected by a medium with higher scalar value, or in our case with higher index of refraction, then the reflected light ray is reversed. So if I try to draw the incident ray like this, then when it is reflected, it has an opposite phase or a phase lag of lambda over 2. If medium 2 has a higher refractive index than medium 1, then the reflected ray will be out of phase or will have a path length difference of lambda over 2. However, when the second medium has a lower refractive index than the first medium, then the reflected light ray will have the same phase as that of the incident ray. In other words, it can have a path difference of multiple integers of lambda. Now, when it comes to the reflected ray number 2, or the second reflected ray, we could also apply this rule wherein if the third medium has a higher refractive index than medium 2, then this reflected ray 2 here will have a path difference of lambda over 2 with respect to the incident ray. Otherwise, it won't have any phase lag or it won't have any path difference with respect to the incident ray. So apart from that, we should also consider the distance traversed by this ray 2. So apparently, ray 2 traversed this extra distance in comparison with the first reflected light ray. If this medium here has a thickness of T, so let me write it here. So if this medium has a thickness of T, so basically when light ray enters this portion, then it is reflected back. If this thickness T is greater than the wavelength of light, usually this is in the millimeter to micrometer scale, while the wavelength of light is in the micrometer scale or 100 nanometer scale. We could actually consider this as if the light ray bounces in a perpendicular manner. So essentially, we could just neglect the angle of incidence here and the angle of reflection as if the length of the distance that this light ray traversed is almost the same as if it enters in a parallel fashion. And when we assume this behavior of light, we could actually simplify the calculation and let's just approximate that this distance is represented by 2t. In other words, light simply enters the film at a distance t, and then it is reflected back at a distance t. So we have t here and then another t here, then we have 2t, a distance of 2t. So essentially this light traverses a distance of 2t, and this time if we observe a very bright color coming from the soap bubble, then this means that if light ray 1 has a path difference of lambda over 2, then for constructive interference to occur, ray 2 must displace a path 2t that is equal to lambda over 2, assuming that it did not undergo a phase change like this one. Essentially, if this is air, medium 1 is air, just like in our example of bubble, we have air, water, air. The medium for n sub 2 consists of water. So basically, if we have air, water, and air, then apparently this reflected wave will be in phase. In other words, it won't have a phase lag or a path length difference of lambda over 2. So here, for constructive interference to occur, if ray 1 has a path difference of lambda over 2 with respect to the incident ray, then this reflected ray on medium 2 must have a path difference of lambda over 2 so that the interference pattern produced by ray sub 1 and ray sub 2 will result to a constructive interference. Otherwise, if reflected ray 1 has a path difference of lambda over 2 and we observe that it produces destructive interference, then ray 2 must traverse a distance, a total distance that is equal to an integer multiple of lambda. So that when they undergo interference, they will produce a dark region or a destructive interference pattern. So to generalize this first one, 2t must be equal to m plus 1/2 times lambda. And m here is just an integer that can be equal to m equals 0. That means at m equals 0, we're actually looking at the first 0th order bright pattern. And if m equals 1, if we look at the intensity pattern like this. So at m equals 0, we're actually looking at the 0th order maximum, and if m equals 1, we're actually looking at the first order maximum of the interference pattern, and so on. When solving problems involving thin films, we must always consider whether the reflected wave has a path difference of lambda over 2 with respect to the incident ray. This has to be applied for both reflected ray 1 and reflected ray 2. And also, the distance traversed by the light ray 2 in medium 2 must also be monitored whether it will result to a path difference of m plus 1/2 times lambda or an integer multiple of lambda. So this will become apparent when we try to solve problems involving thin films. As an example, this problem is from OpenStax University Physics Chapter 3 Interference Problem 31. In a double-slit experiment, the fifth maximum is 2.8 centimeters from the central maximum on a screen that is 1.5 meters away from the slits. If the slits are 0.15 millimeter apart, what is the wavelength of the light being used? So to visualize this is our slits, and let's assume that the central maximum is at this point. So we could actually draw this way. And the second maximum is at this point. There's also a second maximum here, but I won't draw it. This is just for demonstration purposes. Always remember that interference patterns are symmetric. So if we have a first maximum here, there should also be a first maximum here. So, but I'm just going to draw the upper half of the interference pattern. So the second maximum is right here. And let's assume that the third maximum is right here. The fourth maximum is right here. And finally, let's assume that the fifth maximum is right here. And based on the given, it is 2.8 centimeters away from the central maximum. And the distance of the slits, let's represent it as D. According to the given, D equals 0.15 millimeters. The question is, what is the wavelength of the light being used? When we illuminate this with light, it produces an interference pattern wherein the fifth maximum is at y equals 2.8 times 10 raised to negative 2 meters away from the central maximum. So this screen also is at a distance capital D away from the slits, and D equals, based on the given, is 1.5 meters. So first of all, in order to produce a bright pattern or a maximum, the path difference of the two rays here should be an integer multiple of their wavelength. And if m equals 0, we're actually looking at the central maximum or the zeroth order maximum. And since we're dealing with the fifth maximum, m here is actually equal to 5. And based on our derivation, the path difference is actually equal to d sine theta equals m lambda. Now notice that if I try to separate this right triangle here, we have y and then d, and this is theta. And this theta is the same as the sine theta in this expression. So to get theta, observe that tangent based on this triangle, tan theta is equal to opposite, which is y, divided by adjacent, which is d. So to get theta, this is actually equal to theta equals arctangent of y over d. And then I can plug this back to sine theta. And we're actually looking for the wavelength, so I can arrange this in terms of wavelength. Rearranging this in terms of wavelength, I have lambda equals d sine theta over m. But again, theta is equal to arctangent of y over d. D over m times sine of arctangent of y over d. And plugging in the values, and I'll end up with lambda equals 560 nanometers. Let's have an example involving thin film interference. A soap bubble is 100 nanometers thick and illuminated by white light incident perpendicular to its surface. What wavelength and color of visible light is most constructively reflected, assuming that the film has the same index of refraction as that of the water? So here we have soap bubble. And then if we try to magnify this portion, it looks like this. So this is actually the liquid part of the bubble, and it is being sandwiched by air molecules above, outside, and we assume that inside this soap bubble is just a bunch of air molecules, so that the pressure inside and outside are almost the same and the bubble will not burst So again, if this is the eye of the observer, some of the incident light will be reflected at the outer surface of the film, and some of the light will be able to pass through this boundary, but upon hitting the inner boundary of the film, it's also reflected. And before reaching our eyes, it produces an interference with ray 1. So let's call this ray as incident ray, and this one as ray 1, and this ray as ray 2. Again, in the problem, we assume that ray 1 and ray 2 will undergo a constructive interference. Now, let's represent the refractive index of air as N sub air, while the refractive index of water is N sub W, and also the refractive index of this side is also N sub air. Now, ray 1 is a reflected ray, and obviously, since the refractive index of water is approximately 1.33 and the refractive index of air is approximately equal to 1.00. Since the refractive index of water is greater than the refractive index of air, then ray 1 actually has a path difference of lambda over 2. Since we are hoping for a constructive interference between ray 1 and ray 2, and assuming that the thickness of this film or soap bubble film is T. Since the incident light hits the surface in a perpendicular manner, then essentially this ray 2 before leaving the film actually traverses a distance of 2t. Since it actually hits the film in a perpendicular manner, so at this point it traverses a distance of t, and then it is reflected back at a distance of t. So my illustration here is actually an exaggeration because the eye should be looking at this angle so that the light ray is almost perpendicular with respect to the surface. In order for ray 1 and ray 2 to undergo constructive interference, the path that must be traversed by ray 2 must result to a path difference of lambda over 2. So essentially, when ray 1 leaves this surface, it has a path difference of lambda over 2. And when ray 2 leaves this surface, it must have a path difference of lambda over 2. So if ray 1 has a path difference of lambda over 2 with respect to the incident ray, and if ray 2 has a path difference of lambda over 2 with respect to the incident light ray, then ray 1 and ray 2 actually has a path difference of 0. With this condition, constructive interference occurs. So we could actually use this relationship in order to calculate for lambda. And we are asked to find the wavelength of a visible light, and it doesn't clearly state whether we should calculate the wavelength inside the film or in vacuum or in air. By default, we're actually calculating for the wavelength in air. And since wavelength in air and wavelength in vacuum are almost the same, because the standard wavelength of light, visible light presented in textbooks, are actually wavelength measured in air or in vacuum. So we're actually looking for the wavelength in air. But we are given with this numerical value, so we would like to derive an expression for wavelength in terms of these given values. So recall that the definition of refractive index, it is the ratio of the speed of light divided by the speed in a medium. And notice that the velocity of any wave is actually equal to its wavelength divided by the time it takes for it to complete one wave cycle or period. And period is just the reciprocal of frequency. So I could actually plug this here. So N equals C over lambda F. And I could actually rewrite this as N lambda equals C over F because the speed of light is always constant and it's equal to 3 times 10 raised to 8 meters per second, and the frequency of light remains the same whether the wave travels in air or the wave travels in water. So essentially, this factor here is constant. When the wave travels in air, we could just represent its refracted index as N sub air and its wavelength as lambda sub air, and it's equal to a constant C over F. Again, the frequency of the light wave remains constant whether it's passing through a medium of lower refractive index or a medium with high refractive index. When light ray enters the film, we could represent its refractive index as N sub W and its wavelength as lambda sub W and also equal to a constant. Since these expressions are equated to the same constant, we can equate the two. N sub air times lambda sub air equals N sub W lambda sub W. Now notice that this distance is being traversed by the light when it is inside this film. So essentially, this wavelength here is actually the wavelength when the light ray is inside this film, which we designate as lambda sub W. So let me rewrite this expression here. 2t equals lambda sub W over 2. So I'll arrange this in terms of lambda sub W so I can plug it here. I'm going to plug this here. So I'll end up with 2t equals n sub air lambda sub air divided by 2 n sub W. Here our target variable is lambda sub air, so I'm going to arrange it in terms of lambda sub air. Lambda sub air equals 4t n sub W over n sub air, which is approximately equal to 1. Plugging in the given, the thickness is 100 nanometers times n sub W, which is approximately 1.33, divided by the refractive index of air, which is 1.00. So I'll have lambda air equals 532 nanometers. This actually corresponds to a green color because it's near the wavelength of green. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!